So, we are going to now understand the properties of this class S star. Okay. What are the properties of this collection of measurable sets? So, the first observation is that every set in the given algebra is measurable. That means, if A belongs to the algebra A, then this condition is always going to be true. So, let us verify that. So, let us show that if A belongs to the algebra, then A is measurable, and that is for every y a subset of x with mu star of y finite. We should have mu star of y is bigger than or equal to mu star of y intersection E, y intersection A, sorry, the set is A. So, y intersection A plus mu star of y intersection A complement. So, this is what we have to show. So, let us look at the proof of this. Now, we are going to use the fact that mu star of y is finite, and mu star of y finite means that it is a infimum of some quantities. So, that crucial definition, what is definition of infimum, we are going to use. So, let epsilon greater than 0 be fixed. Then by definition of infimum, there exists a covering. So, there exist sets A I belonging to A with the fact that the set y is covered by union of A i's I equal to 1 to infinity, and mu star of y, which is infimum plus a small number, does not remain the infimum. So, it is bigger than or equal to mu of A I equal to 1 to infinity. Right. So, here we are using the fact that mu star of y is infimum, and that is a finite quantity. Now, A i's are in the algebra, A is in the algebra. So, I can write this as, this is equal to sigma I equal to 1 to infinity mu of union of A i's intersection E intersection A, sorry, the set is A 1 to infinity union of the sets union I equal to 1 to infinity A I intersection A complement. So, what I am saying is sorry, not the union, this is wrong. So, let me just simply write it as. So, let us observe what we are saying. We are saying because of this each set A I. So, let us note A I can write as A I intersection A union A I intersection A complement, and these are two disjoint sets, and mu is a measure, all the A i's A, everything is in the algebra. So, using the fact that mu is a measure, I can write it as, so implies that mu of A I is equal to mu of A I intersection A plus mu of A I intersection A complement, right. So, now mu of A I intersection A complement. So, that means summation mu of A I equal to 1 to infinity is equal to summation I equal to 1 to infinity mu of A I intersection A plus summation I equal to 1 to infinity mu of A I intersection A complement. And now, let us note that the set A intersection y is covered by union of A I intersection A I equal to 1 to infinity, because y is covered by union of A i's. So, A intersection y is covered by this, and A complement intersection y is covered by union of I equal to 1 to infinity A I intersection A complement, and these are sets in the algebra, because A belongs to the algebra, that is a crucial thing. So, this will imply that mu star of A intersection y is less than or equal to summation of mu A I intersection A complement I equal to 1 to infinity, and mu star of the second one gives me A complement intersection y is also a is less than or equal to, using this summation I equal to 1 to infinity mu of A I intersection A complement, right. So, look at this equation, look at this equation, look at this equation. So, mu star of summation mu star of A I is bigger than this sum, and that sum is bigger than or equal to mu star of A intersection y, and this sum is bigger than or equal to mu star of A intersection y, A complement intersection y, and we had mu star of y plus epsilon was bigger than this summation. So, that summation. So, putting these three equations together. So, if we call that earlier equation as 1, call this equation as 2, call this equation as 3, and call this equation as 4, then putting all these 4 equations together, what we have is the following, that mu star of y plus epsilon, which was bigger than or equal to summation mu star of A I equal to 1 to infinity, that is equal to actually summation of mu star of A I intersection A I equal to 1 to infinity plus 1 to infinity mu star of A I intersection A complement, and that is bigger than or equal to mu star of y intersection A plus mu star of y intersection A complement. And now, epsilon is arbitrary. So, let epsilon go to 0. So, this inequality will be still maintained, will imply that mu star of y is bigger than or equal to mu star of y intersection A plus mu star of y intersection A complement, and that will imply that A belongs to S star, that is A is a measurable set. So, that is, so hence we have proved that the algebra A is included in the collection S star. That is what we wanted to prove. So, this is the proof of the fact that the algebra A is contained in S star. Every element of A is measurable. The next property, that the class of measurable sets is closed under complementation, namely if E is measurable, then E complement is also measurable. That is obvious, because in this criteria, if you want to check if E is measurable, then this is what we required, and to check E complement is measurable, the same thing is required, because this will become E complement, and E complement of complement is E. So, it is the same criteria, same equation to be verified. So, obviously, because the definition has inbuilt E and E complement symmetric with respect to E and E complement, that says the set E is a set E is measurable if and only if its complement is measurable, or the collection S star of measurable sets is closed under complements. Next, we want to check the property. So, the collection of all measurable sets, 1, it includes the class of all subsets in the original algebra A, and we want to check now that it is an algebra of subsets of X. That means, and mu star restricted to S star is finitely additive. So, two things we want to check: 1, S star is an algebra, and mu star restricted to S star is finitely additive. So, let us see what we have to check for this. So, first of all, we want to check that S star is an algebra. We have already shown A is inside S star. So, that implying the empty set and the whole space that belong to A, and hence A is in S star. So, empty set and the whole space belong to it. We just now observed that E belonging to S star implies E complement belongs to S star. So, if E is measurable, E complement is measurable, that also we have checked. So, let us check the third property, namely if E1 and E2 belong to S star, we want to check this implies E1 union E2 also belongs to S star. That means, union of measurable sets is again measurable. So, this is what we want to check. So, let us look at a proof of this. To check that E1 E2 is measurable, we have to check for every y contained in X, mu star of y finite. We have to check that mu star of y can be written as mu star of y intersection the set, that is E1 union E2 plus mu star of y intersection E1 union E2 complement. So, this is the property that we have to check. So, what we will do is we will compute each one of the term and show it is equal to mu star of y. So, for that we start. So, note E1 is measurable. So, that implies that mu star of y, we can write it as mu star implies for every y, mu star of y is mu star of y intersection E 1 plus mu star of y intersection E 2. And now, this is important that this happens for every y. So, I can change y according to my requirements. Okay. So, what I want to do is I will change this y to y intersection E 1. See, I want to compute y intersection E 1 union E 2. So, let us change it this y to that. So, that implies that mu star of y intersection E 1 union E 2 is equal to, here I should replace y by y intersection. So, mu star of y intersection E 1 intersection E 1 union E 2, but E is a subset of E 1 union E 2. So, that is just y intersection E 1. Is that clear? Because if I replace y by y intersection E 1 union E 2, then this intersection with y 1 with E 1 is just y intersection E 1 plus what is the second thing, let us write. So, mu star of this one is E 1 complement. I am sorry, we made a mistake saying it is measurable. Mu star of y is mu star of y intersection E 1 plus mu star of y intersection E 1 complement. And now, when we replace y by y intersection E 1 union E 2. So, this is same as this plus the second term is y intersection E 1 union E 2 intersection E 1 complement. Right. So, let us simplify that. So, what we have gotten is the following. That mu star of y intersection E 1 union E 2, that was the left hand side, is equal to mu star of y intersection E 1 plus what is this? Now, E 1 union E 2 intersection E 1 complement. So, when I take E 1 complement, that is going to be empty set. So, this set is nothing but mu star of y intersection E 2 intersection E 1 complement. Right. So, we have computed mu of y intersection E 1 union E 2 to be equal to this. And now, I also want to compute what is mu star of y intersection complement of this. So, what is the complement of this? E 1 union E 2 complement. So, what is that going to be? That is going to be mu star of y intersection by using our proper De Morgan laws for set theory. This is E 1 complement intersection E 2 complement. So, I want to compute mu star of E 1 complement intersection E 2 complement. How can we compute that? Recall saying that E 1 was measurable, we had that. So, if I replace y by y intersection E 2 complement, then I will get the required set here. So, use this equation. So, since E 1 is measurable, we have mu star of y. So, we will just keep it here to follow. So, mu star of y intersection, I want instead of this we want y intersection E 2 complement. So, let us look at y intersection E 2 complement is equal to mu star of y intersection E 1 intersection E 2 complement plus mu star of what will be this set y intersection E 2 complement intersection E 1 complement, right. So, that is what we will have. Okay. So, this is what I wanted. Now, let us observe in this equation all the numbers are real numbers, because of the assumption that mu star of y is finite. So, this is a subset. So, this is finite, this is finite, this is finite, all are finite numbers. So, I can interchange them, I can take one term on the other side if required. So, let us do that. So, from here we compute. So, implies mu star of y intersection E 1 complement E 1 complement intersection E 2 complement. This set is equal to mu star of y intersection E 2 complement minus, take it on the other side, it is mu star of y intersection E 1 intersection E 2 complement. Okay. So, we have gotten the required quantities. Okay. So, we wanted mu star of, we wanted what is mu star of y intersection E 1 union E 2. So, that is lying here. And we wanted, that is lying here, the second term. So, let us add these two terms. So, adding, so add, call it as this equation as 1, call this equation as 2, add 1 and 2, and that will give you that mu star of y intersection E 1 union E 2 plus mu star of y intersection E 1 complement intersection E 2 complement. So, this is equal to, there we have got y star mu star of y intersection E 1 plus mu star of y intersection E 2 intersection E 1 complement plus y mu star of y intersection E 2 complement minus mu star of y intersection E 1 intersection E 2 complement. Okay. So, this is what we have gotten, and we want to check that this should come out to be equal to mu star of y. Okay. Now, let us again try to use. So, this is mu of intersection E 2 complement here, and that is E 1 intersection E 2 complement. Okay. Now, let us observe till now we have not used anywhere the fact that E 2 is measurable. Okay. So, let us try to use that fact that E 2 is also measurable, and so that we can simplify this quantity. So, now observe E 2 measurable implies the following fact. We want to simplify this. So, let us look at what is going to be E 2 y intersection E 2 and y intersection E 2 complement, right. So, let us try to E 2 measurable means, so for every y we have got mu star of y is equal to mu star of y intersection E 2 plus mu star of y intersection E 2 complement, right, because of measurability. Now, I want to use this to compute one of the terms here. So, let us replace y by y intersection E 2. So, that implies I can replace this by mu star of y intersection E 2 will be equal to that will not give us anything. Let us replace this by y intersection E 1. So, implies mu star of y intersection E 1 is equal to mu star of y intersection E 1 intersection E 2 plus mu star of y intersection E 1 intersection E 2 complement. Okay. So, what is mu star of y intersection E 1 intersection E 2 complement? That term is here. Okay. So, that we want with a negative sign. So, if I take it on the other side, so that means minus mu star of y intersection E 1 intersection E 2 complement is equal to, I bring it on the other side. So, that is minus mu star of y intersection E 1 plus mu star of this term, which is y intersection E 1 intersection E 2. Okay. And now, this, so this is what we have reached here. So, this is the value that I was looking for. So, let us put in this value. So, this required quantity, I will just take it here, is equal to, so this required quantity is equal to mu star of y, okay, and here is minus mu star of y. So, those two terms will cancel out. Okay. So, let me just write, that is mu star of y intersection E 1 plus mu star of y intersection E 2 intersection E 1 complement, that we already had. So, plus mu star of y intersection E 2 complement and minus. So, that is equal to minus mu star of from here y intersection E plus mu star of y intersection E 1 intersection E 2, and now these two terms cancel out. Okay. So, what we are left with is, so this is equal to mu star of y intersection E 2 intersection E 1 complement and y intersection E 2 intersection E 1. So, look at these two terms. So, these two terms, it is y intersection E 2 intersection E 1 complement plus y mu star of y intersection E 1 and E 2. Okay. So, that means, so these two terms are nothing but mu star of y intersection E 2. So, and one term is here. So, this is mu star of y intersection E 2 plus, what I am saying is that this plus this term is nothing but mu star of y. So, this is complement mu star of y intersection E 2. Is that clear? This term as it is. Now, look at the fact that E 1 is measurable. So, mu star of y intersection E 2 is mu star of y intersection E 2 intersection E 1 complement plus mu star of y intersection E 1 intersection E 2. And now, once again using the fact that E 2 is measurable, that is equal to mu star of y. So, we have proved the required condition that mu star of y is equal to mu star of y. So, we have proved that this is mu star of y is equal to mu star of y intersection E 1 union E 2 plus mu star of y intersection E 1 complement intersection E 2 complement. So, that means, we have proved the fact that S is an algebra of subsets of the set X. So, what we have shown is E 1 E 2 belonging to S star imply E 1 union E 2 also belong to S star. Here, let me just comment that this proof looks a bit technical, but it is not so difficult. E 1 measurable gives you one condition, that mu star of y is equal to something. Okay. E2 measurable gives you mu star of y is equal to something. Now, these sets y are arbitrary. When you are given E1 and E2 are measurable, means mu star of y is equal to mu star of y intersection E1 plus mu star of y intersection E2 E1 complement. So, you can change this y to y intersection E1, y intersection E2 and so on. So, write down the three equations which are given, write down the equation the equality that we proved, and just manipulate. This is only a simple algebra which is required. So, today what we have done is we have looked at, we have defined the concept of what is called a measurable set for a outer measure mu, and we have shown that the original elements of the algebra are already measurable sets, and the class of all measurable sets form an algebra. So, we will continue the analysis of this class S star in our next lecture. Thank you.